Visual representation of Cartesian products. So far we've discussed what Cartesian products are, how we take two sets and create a new set of ordered pairs. Now, we're going to move on to how we can better understand them. This slide introduces the idea of visually representing these Cartesian products. We'll be using two main tools, tables and grids. Think about it, when we started, we were just listing out ordered pairs. That works fine for small sets, but as the sets get bigger, it becomes really easy to make mistakes or miscombinations. That's where these visual tools come in. The main goal here is to help you see how elements from one set are paired with elements from another set to form those ordered pairs. By visualizing it, it will solidify your understanding of the whole process. We're essentially taking an abstract concept and making it more concrete. In the following slides, we'll walk through exactly how to create these tables and grids, and we'll work through some examples. So, pay close attention, because this is a really helpful way to make sure you've truly grasped the concept of Cartesian products. Understanding the need for visual representation. If we tried to list all the possible ordered pairs manually, it would quickly become a very long list, and honestly, quite easy to make mistakes. You might accidentally repeat a pair, or worse, forget to include one. That's where visual representations come in. This slide highlights that a table or a grid, which we'll explore in detail on the following slides, provides a much clearer and more organized way to see every possible combination. It's like having a map of all the ordered pairs laid out neatly before you. By visualizing the Cartesian product, it becomes significantly easier to grasp the underlying concept and, crucially, to avoid missing any of those ordered pairs. We want to be absolutely sure we've accounted for everything, and a visual aid really helps with that. So let's move on to slide 2. As we discussed on the previous slide, the Cartesian product is all about combining elements from two sets to create ordered pairs. Now, imagine those sets aren't tiny. Let's say they each have 4 or 5 elements. So, keep this in mind as we move forward, because we're going to see how to create these tables and grids to represent these combinations effectively. Using tables to represent Cartesian products. So now that we've discussed why visual representations are helpful, remembering that listing out all the ordered pairs can get messy quickly, let's dive into how to create these visuals. This slide focuses on using tables, and it breaks down into 2 main steps. We're going to create a table, and the first thing we do is label the rows and columns. The elements of our first set, which we're calling set A, will become the headings for each column across the top. And the elements of our second set, set B, will be listed down the first column as row headings. So, essentially, we're creating a grid where each row represents an element from set B, and each column represents an element from set A. Now, step 2, fill in the table. This is where we actually start forming the ordered pairs. Remember, the Cartesian product is all about pairing each element from set A with each element from set B. Each individual cell within the table represents one of these unique ordered pairs. Let's say you're looking at a specific cell in the ITH row and JTH column. The ordered pair that this cell represents is formed by taking the JTH element from set A, that's the column heading, and pairing it with the ITH element from set B, that's the row heading. So, it's a combination of the row and column labels. Keep in mind, as we move on to the next slide with an example, that this systematic approach ensures we don't miss any possible combinations. And as we'll see later, while this works great for smaller sets, it becomes less practical as the sets get larger, but the underlying principle remains the same. Example using tables. So let's solidify our understanding of Cartesian products with a concrete example. On this slide, we're going to use a table to visually represent the Cartesian product of two sets, A and B. First, we define our sets. Set A contains the elements 1 and 2, that is, A equals the set containing 1 and 2, and set B contains the elements A and B, that is, B equals the set containing A and B. Now let's build our table. As we discussed on the previous slide, the first step is to set it up. We write the elements of set A across the top row as column headers, so we have 1 and 2. Then we write the elements of set B down the first column as row headers. That gives us A and B. Notice the empty cells, these are where we'll build our ordered pairs. Next, we fill in the table. Remember, each cell represents a unique ordered pair. To find the ordered pair for a specific cell, we combine the element from the corresponding row with the element from the corresponding column. So in the first row and first column, we have A and 1. This gives us the ordered pair 1A. In the second column of the first row, we have A and 2, which gives us the ordered pair 2A. Moving to the second row, in the first column, we have B and 1, giving us the ordered pair 1B, and finally, in the second row and second column, we have B and 2, which gives us the ordered pair 2B. Therefore, the Cartesian product of A and B, written as a cross B, is the set containing all these ordered pairs. 1, a 2, a 1B, and 2B. Keep in mind, as we'll see in later slides, this method is great for smaller sets. When the sets get larger, it becomes less practical to list everything out, but the underlying principle remains the same. We're simply combining each element from the first set with each element from the second set to create all possible ordered pairs. Using grids to represent Cartesian products. So we've just seen how to represent Cartesian products using tables, which was a really organized way to list out all the ordered pairs. Now, let's explore another visual method, using grids. This slide introduces the idea of representing Cartesian products with a grid, and this method becomes particularly helpful when the elements within our sets can be thought of as coordinates. Remember, coordinates are how we locate points on a plane, and that's exactly what we'll be doing here. Now, let's break down the process into 2 key steps. Step 1, define the axes. Think of a standard coordinate plane. You have a horizontal line and a vertical line that intersect. We're going to use that same idea. We need to decide which of our 2 sets will represent the x-coordinates, which are the values along the horizontal axis, and which set will represent the y-coordinates, the values along the vertical axis. Once you've made that decision, simply draw your x and y axes. Step 2, plot the points. For every ordered pair that we found in the Cartesian product, remember, an ordered pair has the form x, y. We're going to plot that point on our grid. So, we take the first element of the ordered pair as the x-coordinate and move that distance along the x-axis, and then we take the second element as the y-coordinate and move that distance up or down along the y-axis. Where those 2 lines meet is the point representing that ordered pair. Keep in mind that in the next slide, we'll work through a specific example to show you exactly how this looks in practice. And as we move forward, remember that while tables and grids are great for smaller sets, the core idea of combining elements to form ordered pairs remains the same, even with larger sets. Example using grids. Let's move on to visualizing Cartesian products using grids. As we discussed earlier, tables are great for smaller sets, but grids become particularly useful when we start thinking about these ordered pairs as coordinates on a plane. So, on this slide, we have 2 sets defined. A and B. Set A contains the elements 1 and 2, and set B contains the elements 3 and 4. We're going to treat set A as providing our x-coordinates and set B as providing our y-coordinates. Now, remember from the previous slides, to find the Cartesian product, we combine each element of A with each element of B, so, across B, that's A times B results in the following ordered pairs: 1, 3, 1, 4, 2, 3, and 2, 4. Essentially, we've created all the possible pairings. Finally, let's visualize this. We'll plot these ordered pairs on a grid. Imagine a standard xy coordinate plane. For the first ordered pair, 1, 3, we locate the point where x equals 1 and y equals 3 and mark it on the grid. We repeat this process for each of the ordered pairs, 1, 4, 2, 3, and 2, 4. Each of these points you plot represents one of the ordered pairs we found in the Cartesian product. This grid visually demonstrates how the elements of sets A and be combined to form all possible ordered pairs in a cross B. Keep in mind, as we move forward, that while this is a great way to see the combinations, for much larger sets, actually plotting all the points becomes impractical. But the underlying principle, every element in the first set paired with every element in the second set, remains the same. Larger sets and visual representation. Let's move on to slide 7. As we've seen, we've been using tables and grids to visualize Cartesian products, and that's been really helpful for understanding how the combinations work, especially with smaller sets. But what happens when our sets get bigger? This slide points out that tables and grids become less practical when dealing with larger sets. Imagine trying to draw a grid with, say, 10 elements in each set. It would be enormous and quite messy. However, the underlying principle doesn't change. Remember, the Cartesian product is all about taking every possible pairing of elements from two sets. So, even with larger sets, each combination of one element from the first set and one element from the second set still forms a unique ordered pair within the Cartesian product. Now, instead of trying to list or plot all those ordered pairs when the sets are large, we shift our focus. We start thinking about how many ordered pairs there would be, and that's where the size of the sets comes in. If set A has m elements and set B has n elements, then the total number of ordered pairs in the Cartesian product across B, and I'm saying cross as in a times B, is simply m multiplied by n, so the total number of ordered pairs is the product of the sizes of the two sets. This is a crucial takeaway. While visualizing is great for building intuition, for larger sets, calculating the number of ordered pairs becomes the more efficient approach. This will be important as we move forward and encounter more complex problems involving Cartesian products, and will rely more on this calculation than on drawing out every single pair. And that brings us to the end of the core concepts. The next slide will summarize everything we've learned and highlight some common mistakes to avoid. Key takeaways. So, as we've seen through using tables and grids, visual representations are incredibly helpful in understanding how elements from two different sets combine to form those ordered pairs that make up the Cartesian product. Remember, the Cartesian product takes elements from set A and pairs them with elements from set B, creating a new set of pairs. The visuals just make that pairing process much clearer. Specifically, each cell within a table, like the ones we constructed earlier, represents one of those unique ordered pairs. And similarly, each point we plotted on a grid also corresponded to a single ordered pair. So, whether you're using a table or a grid, you're visually mapping out all the possible combinations. Now, we touched on this briefly on the last slide, but it's important to remember that this principle of combining elements to form ordered pairs doesn't change just because the sets get bigger. Whether you have sets with 2 elements or sets with 20, the fundamental idea remains the same. While it might become impractical to draw a table or grid for very large sets, the underlying concept of pairing each element from one set with each element from the other still holds true. We then focus on calculating the total number of ordered pairs, which is simply the product of the number of elements in each set. Let's recap what we've learned about Cartesian products with this final slide on visual representation. This brings us to the end of this section on visualizing Cartesian products. Hopefully, these tables and grids have given you a solid understanding of how these combinations work. In the next section, we'll move on to explore some of the properties of Cartesian products and how they relate to other set operations. Common mistakes. First, let's talk about reversing the order. Remember, when we form ordered pairs, the order absolutely matters. So, a pair consisting of A and B, which we would say as a comma B, is completely different from a pair consisting of B and A, which we would say as B comma A. It's not just a matter of preference. They are distinct ordered pairs and will have different positions when we represent the Cartesian product visually, like in our tables or grids. So, always double-check that you're mapping the elements in the correct order when you're creating those pairs. Next, we have missing combinations. When dealing with even moderately sized sets, it's easy to accidentally leave out an ordered pair. That's why the systematic approach of filling in a table or carefully plotting points on a grid is so helpful. By working through each element of the first set and pairing it with each element of the second set, you can ensure you haven't missed any possible combinations. Think of it like a checklist, methodically going through each row and column. Finally, and this is a big one, is confusing the Cartesian product with set union or intersection. These are all set operations, but they do very different things. Remember, the Cartesian product isn't about combining elements within a single set. Instead, it's about creating ordered pairs by taking one element from each of the two sets. Set union, on the other hand, combines all the unique elements from two sets into a single set. And set intersection finds the elements that are common to both sets. So, the Cartesian product results in ordered pairs, while union and intersection result in sets of elements. Let's move on to the final slide, which highlights some common mistakes students make when working with Cartesian products. Understanding these pitfalls will really solidify your grasp of the concept. Keep these common mistakes in mind as you practice, and you'll be well on your way to mastering Cartesian products.